Today, if I am correct, I am going to prove that the current agreed solution is not correct. When I search on YouTube, 100% of the videos are saying that switching has more chance than staying to pick the price door. There is none that says the chances are the same. Probably I have not searched for long enough, but today I made this video to try to prove that both switching and staying are of equal chances to get the price door. Hello, thank you for being interested in my challenge on the Monty Hall problem. With this video, if I am right, I am sure it will be beneficial for everybody. If I am wrong, I hope I can understand where I can improve on. So I hope we can learn from each other here. Let's go straight into my views and opinions on this problem. Please don't mind my very simple and basic slides. In this video, I will be talking about these 6 points. A quick recap on the current agreed solution that most people agreed on. Next will be my views on the problem. I will try to prove them correct by using the layman's method before trying to prove the figures used in the formula are not appropriate. I will also briefly touch on my thoughts on probability as a topic on everyday lives, and I will end off with the conclusion. Okay, let's have a quick recap. This is an image from Wikipedia about the Monty Hall problem on the possible outcomes. It gives 100 cases for each scenario of the initial positions so that the probability can be illustrated using a fixed number of cases and assuming that the left door is picked by the contestant at the beginning of the game. By using these 150 cases highlighted in the darker grey box as the sample size, the current solution compares the 100 cases with the other 50 cases to deduce that switching has better chance of getting the prize compared to staying. That's a brief summary. After the recap, here are my views on the problem. This is a chart that I have drawn out, assuming the left door is picked initially. For learning purposes, since there are 2 goats in the question, there should be a total of 6 different outcomes instead of 3 because the 2 goats could switch places. Yes, the results are the same and it also looks the same, but I think this should be the way to learn because every little details are important. About the legend on the right, the letter P represents the prize door, the letter G represents the goats. There is also the double arrow because of the fact that when the prize door is picked, each goat has a 50% chance to be revealed. The single arrow represents the single and only outcome of the revealed door if a goat is chosen at the beginning of the game. The empty vertical rectangular box represents an unrevealed door, and after the arrows, the letter G represents the revealed door that showed a goat. This will be the chart if the middle door is picked instead. This chart represents the outcome if the right door is picked. The position right, not as in right or wrong. If we combine all the 3 charts shown earlier, we will have this summary chart. And here is the thing that I want to talk about. Have you noticed that whenever the prize door was picked initially, it will have a split arrow, the blue regions. And yes, my view is this caused the misleading part that I would like to address in the video. You must be wondering, how is it misleading? Let me explain myself from the next slide onwards. Let me try to prove my views by using the layman's method first. Let us look at this from a different perspective. What are all the possible initial positions of the prize and the goats? If we arrange them in all the possible combinations of the 1 prize and 2 goats given, we will have these 6 possible initial positions. Whichever door is picked, the positions of the prize and the goats stay the same. I am sure we can agree on that. Since 1 door will be revealed, we can look forward to use this information independently that when a door is revealed with a goat, it should give us the biggest hint on the possible initial positions of the prize and the goats. And of course, also the impossible initial positions, which still has to be one of these 6. Agree? Why not we have an example? In this example, door 1 is picked, door 3 is revealed. Since a revealed goat at a position tells us that this revealed door is a goat door, it also directly tells us that this is not a prize door. Therefore, in this example of a revealed door 3, it means that whichever position that has a goat behind door 3 has a chance to be the initial position. And of course, whichever position that does not have a goat at door 3 are automatically eliminated from the picture. Now that we know door 3 is a goat door, we can eliminate D and F from the picture because their door 3 is a price door. So there is no way D and F could be the initial positions. Since it is a fact that door 3 is reviewed with a goat, we can deduce with certainty that only A, B, C, and E are the remaining possible initial positions, shown on the right side of the screen. Does this make sense? And so we have A, B, C, and E. Looking at the outcome, we can conclude that be it staying or switching, both has the same probability of getting the price, which is 50%. This shows that after a door is reviewed with a goat, switching does not have better chance of getting the price than staying. It is the same if the contestant picked another door number and another door is reviewed. You can try that out. And so that was the layman's method. I hope it made sense, but something still troubles me. I have spent a week trying to figure out why his Bayes' theorem's calculation from Wikipedia is totally correct, but the layman's method still makes sense, at least to me. I am sure something is not right. And I have realized it is because the problem did not lie in Bayes' theorem at all. Of course, that's for sure, because the problem lies on the numbers to plug into the formula for calculations. And it is none other than H3, the probability of the host revealing door 3. This is the calculation from the source from Wikipedia again. I think this calculation could be expressed in another way. Before anything, I must repeat, this calculation is correctly calculated, but why do I say that this is inappropriate? Let me explain why. It is about choosing the figures to be used in the formula. I realized that knowing the probability of the host revealing any particular door does not help us in any way in this game, since a goat door will be revealed no matter what. And since the position of the revealed goats tells us no information about where the prize door could be, it can only tell us where the prize door could not be. Make sense? Moreover, using H3 as 50% or half has a flaw because it had neglected that there are still some probability that staying in the initial pick could still win the prize. Because of this half that is used, it incorrectly reduced the sample size of calculation, and I will try to prove it to you. Let's assume 100 cases for each possible initial positions of the prize and goats. In the example shown, there will be a total of 300 cases of the middle door being revealed, referring to outcomes A1, B1, D, and F, highlighted in red, and also 300 cases of the right side door being revealed, referring to outcomes A2, B2, C, and E, highlighted in blue. With this, we can derive the probability of the host revealing either doors is 50%. But what does this 50% actually mean? To me, what this 50% means is if someone walks into the game show room after knowing that the left door is picked, there is a 50% chance that he will see that the middle door is revealed. And of course, there is also a 50% chance that the right side door is revealed. So if someone were to guess which door will reveal, if door 1 is picked, he will have a 50% chance to be correct. And of course, 50% chance to be wrong. This is how this 50% works and how it should be looked at. We can look at it in another way, with 600 cases in front of us too. Here in this slide, on the right side of the screen, I have numbered the cases in multiples of 50 because of the split arrows. With the example of left door being picked and the host revealing the right side door, we can rearrange the outcome as shown. A1, A2, B1 and B2 each occupies 50 cases only because they were from the split arrow. C, D, E and F each occupy 2 slots because they each stand for 100 cases. When the left door is picked, we know that there will be 300 cases that middle door will be revealed and also 300 cases of right side door to be revealed. Let us focus on the second half, cases number 301 to 600. Since our example is about the host revealing the right side door, which is cases number 301 to 600, I have blurred out the rest. And yes, you must have noticed that A1 and B1 are not blurred out. because this is the misleading part I wish to talk about. The calculations from Wikipedia using Bayes' theorem says that the probability of the car in door 2, or in our case is middle door, given that the host revealed door 3, the right side door, and the contestant picked door 1 is 2/3. This 2/3 is derived by using the 200 cases from C and E divided by the total of A2, B2, C and E, a total of 300 cases, because only H3 was looked at when the host revealed door 3. Why do I say that? I said that because the condition of the formula is, the red part, given that the host reveals door 3 when the contestant picked door 1, which is just cases number 301 to 600. However, here it is, for cases A1 and B1, even though the middle door is revealed in these 100 cases, it does not eliminate them from being existence in a game, because when we see that there were 300 cases of door 3 revealed, we know that A1 and B1, these 100 cases, out of the other 300 cases, still has a chance to get the prize if we stay with the initial pick. The 200 cases of outcomes D and F are eliminated from the game because their right side door is a prize door, while for A1 and B1, there are still 100 cases of chance for the contestant to still win the prize if he or she chooses to stay with the initial pick. Let us proceed to the calculation part. And because of this, I have substituted H3 with G3, where G represents goat. So G3 stands for goat behind door 3. I replace H3 with G3, saying that probability of goat in the door 3 instead of saying probability of the host revealing door 3, because when the host revealed door 3, it only tells us one thing, that this is a goat door, which means this is not a prize door. The probability of opening that particular door means nothing. Why is the yellow part equals to 1? The yellow part describes as the probability of goats in door 3, given that the contestant picked door 1 and the car is behind door 2. Here, since we are given that the car is behind door 2, so the other two doors have to have goats, and so the probability of goats in door 3 here is 1. The green part is 1/3 because it is the independent probability of the car in door 2. The blue part is 1/3 because it is a 1/3 chance that the contestant will pick door 1. The purple part is 2/3 because when contestant pick door 1, there is always 2/3 chance that the goat will be behind door 3. And even if no doors is picked first, the probability of a goat behind door 3 or any door is still 2/3. And so we will get half. It means that when the contestant pick door 1 and there is a goat behind door 3, the probability of car behind door 2 is half, or 50%. Let us also calculate the probability of car behind door 1, which means we are staying with the initial pick. As shown, it is also half. And so, I think the above answer should be equals to half, which is to say, the probability of car in door 2 after we know that one of the goats is behind door 3, given that the contestant picked door 1, is half. What do you think? To end off my presentation, here are my thoughts on probability on everyday lives. What I have learned and understand about probability is the outcome will not be the same as theory calculations, because probability only helps us to determine the chance of something happening and not happening, which means probability also helps us to determine whether the risk of happening or not happening is worth taking. For example, it is 7 a.m. in the morning and the weather forecast reports that there is a 10% chance that it will rain today. How should we take this 10%? With this information of 10% chance that there will be rain today, it can help us to make our decision wiser. Here is what I mean. Should we hang our clothes outdoor to dry, or should we dry them indoors? Should we plan an outdoor activity, or should we cancel any planned outdoor activities? I think you get my point. And it is the same if the probability of raining is 90%. And of course, we shall assume that the weather forecast report is of 100% accuracy for simplicity. Next, Does 10% mean it will not rain? Does 90% mean it will rain? So what is the worth that I was referring to? In the same example of 10% chance of raining today, if we hang our clothes outdoors and that 10% happens, what can we lose? Yep, keep those drenched clothes in, wash them again, and hang them again. Is this additional work worth the 10% risk? If your answer is yes, it means it is worth risking. If your answer is no, are you saying that you will only hang the clothes outside when the weather forecast reports as a 0% chance of raining? The answer could also be clearer if the chance of raining is 90%. If we know that there is a 90% chance that it will rain, we should probably dry our clothes indoors because there is a 90% chance that we need to do those additional work if we hang our clothes outdoor. In terms of probability, it is never about the outcome. It is about whether the risk is worth taking. We are taking risks in our daily lives. Most of the things happen with a probability. One last example before we end. What if now in a box there are 1 red ball and 99 black balls? If you pick the red ball, you automatically win $100,000 cash on the spot. If you get the black ball, you will lose the $1 because each try costs $1. Would you play this game? If you would play this game, will you play it every day? Would you spare $1,000 to play it? Or is your budget $10,000? I know this game sounds totally ridiculous and it's too good to be true. I used an extreme case so that we could see the bigger picture clearer. What if the game rules have changed? It still costs $1 each try, but this time, if you get a black ball, you will get a $1 prize. You will lose your $1 if you pick the red ball. Would you play this game? Yes, you are totally right. This would be a meaningless game to play if you would ask me. And I hope I've made my point. Is taking risks with probability considered as gambling? My view is this. If I can afford to lose what I could lose if I lose the game, and at the same time gaining relatively more if I win, this is acceptable gambling. The keyword is relatively. Is $100,000 a lot? To someone who has $200,000, it is half his net worth. To a millionaire, it is only 10% of his net worth. So, it depends on whether you can afford to lose it. Well, we are gambling each day when we cross the roads, eat fish with bones, leaving the house without an umbrella, and the list goes on. Of course, I think it is not worth risking my life to cross the road, but since it is a need, I will do everything I can to reduce the risk to as low as possible. Hopefully zero, because I can't be staying at home the whole day in my whole life. We need to weigh the wins and losses before we take any action on probability. With that, back to our main topic. Since the question of the problem is whether switching increases the probability of getting the prize door after the host reveals a door with goats, I have to say that switching does increase the probability of getting the prize, but it is from 1/3 to half. Of course, staying also does increase the probability of getting the prize from 1/3 to half. And so, it depends whether you are just wanting to answer the question literally or as a whole. If literally, yes, switching increases the probability from 1/3 to half. If as a whole, switching and staying both are of the same 50%. If you have any thoughts or if you spot any mistakes, don't be shy to leave your comments so that we can all learn from each other. Have a good day ahead.